gates, and all other logic consists of these 5 basic gates.
On the laptop, you know, up on the logic gate, it has folder empty.
Oh, it is? Oh, wait, let me pause this. It consists of 5 basic logic functions. And when you get into digital, if you take digital, you'll really, really see that. So we have what we call a NOT. We have AND, OR, NAND, and NOR. Then we can do with relays, we can do what we call an exclusive OR and exclusive NOR, which is basically what we call combinational logic. It's going to deal with different contacts. But those are really, really cool. Create a Boolean expression for logic gates and circuits from a truth table. We're not going to be really concerned with what we call. So what we can do with logic is we can use a math. We call it Boolean algebra. And what we can do is we can set up an equation for a digital circuit. And then we can see if it reduces. And that's what's really, really cool, is that if you can reduce the equation, you're reducing the circuit. Did I tell you about my experience at U.S. Steel in the scale? I know I told you that. We had they bought an electro scale, which is a major manufacturer of digital scale readouts. And they bought the dang thing without an auto zero on it. And this was a truck scale. So trucks dropped, and it was a line scale where they weigh the line that they're going to shoot into the cube box when they make the steel. And they dump stuff on there all the time. So the weight would keep going up on it. And so a scale has an auto zero on it, and what it does, the scale's got a motion detector on it. And what happens is you auto zero it every once in a while until you see motion, and then you stop. And they bought it without that. So I was assigned the task of designing an auto zero circuit. So I came up here. I thought I had to monitor all the digits. There was like 6 of them, and it was a BCD, so that would be 6 times 4. So I was monitoring 32 inputs to fix the motion, and I carried it in there and showed the circuit to my boss, Grady Vines, and he said, "Let's see if it will reduce." And he developed an equation for the circuit, and he reduced that thing down, and it turned up to be like 2 ICs, which is pretty neat. And that thing might still be on the line scale out in the field. So that really showed you the power of this algebra. And what you do, guys, is that you don't, this right here is a symbol. Now, we learn it as what? Plus, because we know math. But in USB, it's the non-inverted signal. So USB uses what we call differential signaling. So it sends the signal 180 degrees out of phase. So if it was sending digital information like this, then the minus wire would be carrying the opposite of it. But we learned it as math. So that's a symbol that we use, and when we use a symbol, it's representing something. So in logic, that symbol represents an OR. So I wouldn't say A plus B, I would say A or B. So that means my output would be true if A or B was true. That makes sense. And of course, our multiplication, A, we don't use X, we use like a dot. We can't use an X because the X is a legal letter. So the symbols that we use for this in logic is an AND. So in logic, we wouldn't say A times B, we would say A and B. So that means both A and B would have to be true before the output was true. And then we got different symbols. So I could set up a math equation with this, and then we use basically the same rules you learn in algebra to reduce the equation. But what's so cool is that when you reduce it, you're actually making your circuit what? Smaller. And that's Boolean algebra. And we're not going to look at that. More advanced logic functions created by combining two or more of the basic gates. So we can do exclusive OR, we can do exclusive NORs, we can make counters, we can make timers, we can make decoders, encoders, multiplexers, demultiplexers, shift registers, one-shots, latches, and it goes on. But all these devices are made out of 5 basic gates, which is pretty neat. And that's why we call them basic gates. So here's the 5 basic gates. We have what we call a NOT. And in logic, we use this symbol right here. So we come over here, we put like a triangle. And we put that. So this is a symbol for a NOT. This is the only symbol that's got 2 names. So we call the circuit an inverter. But the logic is a NOT. So that's the only one that's got 2 different names. So inverter. So if we deal with highs and lows, so 1 would be true and 0 would be a false. That means if I put a 1 in, I get a 0 out. If I put a 0 in, I get a what? A 1 out. Then we have an AND. The symbol for an AND is we draw the shape of a D, and then we put input. Now, if I call these inputs, I'm just going to give them names A, B, and C, C and D. Then A and B and C and D would have to be true or high before the output. This we call that an AND. And we're going to see how we can do this with contact. But the book wants you that. So if I wrote down the equation for this, I'd say A, and we don't have to put the AND, B, C, D. That's why we write that down. So in algebra, if you put 2 expressions together, it means multiply, right? So, OR. An OR, we come over here, and the symbol would be, and to get an AND, you got to have a minimum of 2. You can have a lot, but you got to have at least 2. And so what that means is, we got 4 inputs, so I can put 2 to 4 combinations on this thing. So I can put 16 combinations, but only one of them would cause a true output. An OR, we do it like this. And normally we do it as 2 inputs, but you got to understand it takes a minimum of 2. How many can I have? A lot, right? Minimum of 2. This is an OR. And of course, if I call this A or B, so that means if A goes true or B goes true, the output goes true. And of course, the math equation, here we can't leave it. It would be A or B. A NAND. What we would do is we draw the circle. Same thing, we put a bubble on the output, which means the output is opposite. Then I can put inputs. I'll put 4 again. A, B, C, D. So this says if all the inputs are true, the output would go false, or the output would go low. That makes sense? Now this one, we would say A, B, C, D, and then we put a bar across the whole thing. It means once you get through and you invert your answer. And then a NOR would be this guy right here. So let's put 3 inputs. So here we would say any high gives us a low. We say any true gives us a false. Right? Any 1 would give us a 0. So all of it. So there's the symbols for the 5 basic gates. That make sense? Is that okay? Well, let's drop this down. When we do truth tables, even though, so if I did a truth table shows you all the states you could put on the input and how the output would respond to that. So this is why it's important to know the number of combinations. So with 4 inputs, I could put 2 to the 4th combinations on that sucker, which means my truth table would have 16 entries in the truth table. So truth tables are nice, but you think we got a an LS 7430, which is an 8 input NAND gate. 8 inputs. So it means if I did the truth table for that gate, it would take 256 entries in my truth table. But it says all highs gives me a low. So once you learn those little terms, you don't need a truth table, right? So here I would say high end gives me a low out. Here I would say all highs get a high. So you say the input first. Here I would say any high gives me a high. How many inputs would that apply to? Many as you want, at least 2, right? Here we would say all highs to get a low, or all ones, I like to say highs. And here we'd say any highs to get a low. So if you get, we had a guy, he had a bachelor's degree from some school, and he was coming in, and we were troubleshooting this digital circuit, and he was writing the truth table above each gate. He was drawing the truth table. And I said, you don't need that because that tells you it takes all highs to get a high. And he said, and he had a bachelor's. Of course, y'all know how many degrees I have? How many would you think? And what type of degree do I have? I have an associate's degree. So I'm getting basically the same degree you got. So you learn by experience, right? Luckily I started. We don't have, so that's, if you understand that, all truths to get a true, right? We'll use that for relays. Any true to get a true, right? Any true gives me a false. All truths give me a false. And we'll see how we're going to do this with relay context. Sequential logic, we don't need flip-flops, we're not going to look at. If you get into, if you take AFT 196, we'll look at one-shots and that kind of stuff. We'll get into that too. And by the way, we have a programming language. In PLCs, they use the IEC symbols. And so this gate right here would look just like this. And then I'd come up here and I'd put the symbol for an AND. And that's the way you program. That's the way, in OR, I'd put a watt in there. So this is that language, that function block programming. You program with gates, but you don't use the ANSI signal. So we're using, in this book it covers what we call, and I'll give y'all two, I need to give those to you guys. Because that function block programming, this is the way you program the PLC. You program it with these symbols. And you just wire them like you would wire a circuit. Which makes it real easy for somebody that came up through this to do what? To write PLC programs without even understanding relay logic. Have output that depends on the inputs as well as time. These are synchronous, and we don't need to do that. It requires clocks. And so propagation delay, though, this gets important. We'll even have that with our timers. So originally, the timers in our PLC was done strictly by software programming. And what they found out right off the bat is programs are nice. What the advantage of programs, of course, is they're changeable, right? You understand? But one advantage that hardware has over software is hardware will always be faster. So these timers we're going to be dealing with are going to be software timers. But if I wanted to keep up with like a incremental encoder running a motor, there ain't no way in the world that software timer is going to keep up with that thing. So what they've done now is they've added what they call high speed counters inside the PLC, which is hardware. So they've actually went back to hardware timers, and so I think this guy right here's got 3 in there. So yeah, so they didn't understand that thing until these motors and stuff would run away with it. But propagation delay was basically how long the inherent time, the time delay between when you tell it to do something and it actually does it, right? So like us, I was closing the trunk on a car one time, and I had my car keys in my hand, and when I started, they slipped out of my hand, and I saw those keys slide down the trunk, go right in the trunk, but I couldn't stop because of my watch. They say, by the time you feel like you're burned, you're what? You're burned. Because because of our propagation. Flip-flops, these are going to be what we call our one-shots and stuff like that, but we're not going to get into that this semester. This would be kind of like we would program in function block program. These are JK flip-flops. You get into those in digital. We have no need for those here. I don't know why the guy teaches it. Boolean expressions. This is when we create a math formula using the different equations. And then what we can do, so the Boolean expression is like a math expression. And then Boolean algebra would be basically the rules that we do to reduce them. And you'll get a little feel. We don't really teach that much even in digital because we just don't need it that much, right? So the book gets into a lot more detail than we're going to get into. What we're going to do, true states, high states, logic highs, false states, ones, zeros. Everybody understand those terms? So I could use high, I could use true, I could use false, I could use zero, and every one of those would mean the same thing. We okay? So rungs, we'll talk about a rung being true. The output of a logic being true. So before your output goes true, then the rung has to be what? True. So we'll use that term a lot. A logic high represented by the presence of voltage, potential, or on an input. Usually represented with 5 volts, and that's not exactly true. Some PLCs deals with 5 volts, but almost all your PLCs now are looking at looking at 24 volts. So that's pretty standard of power supply. So this guy right here, that's what we're using. 24 volts, not only on the input, but also the output. That's why I'm not sure to put my hands up here. So I can't use it connection. Low represented by the absence of voltage, potential, or input, represented by 0 volts, but we're not going to call it. I might call it low, I might call it high. But in this class, we're going to use the term true. Because we're going to be hooking relays, and I'm not going to say if the relay is closed. I'm going to say if the output is true, and then we're running on trying to get what? The whole rung true. If the rung is true, then the output, then whatever we're using is an output. So true table, and this is what we're talking about. So this is the true table. So what you have to do, so 1, 2, 3, it's got 3 inputs. So it means I'd have to have 2 to the third entries in my true table, which would be A. And all we do is we just count. That's where the true table runs. So the output over here, this is the input. We put our inputs on the left. Normally, we use lowercase, we use A towards Z for input, and we use Z toward A for output. So all your output, so you can see that. So A, B, C, and output would be Y or Z or X or something like that. And what we do is basically we just count. And then, so I know so this would be 0, 1, 2, 3, 4, 5, 6, 7, 7. And that's what we put on the input. And then we put how the output would correspond to that. And then we develop an equation. By the way, they could do this, so this means not. So I've got an output. My output is true over here. Right? I need to be doing this while I'm recording. So my output would be true over here. So we would say, not A, so this is what it should be. He's using a letter asterisk, not B and C. So not means it's what? Low. And then I would come over here and I would say, what would be the next true? It would be not A, B, and C. And then my next true would be A, B, B, not C. And then my last one would be or ABC. Now I can look at that and I can tell that sucker's going to reduce. Yeah, because they're all ABC. Oh, well, it's still, you can rearrange it, and you're right, I should put it down there, but you got to understand, 2 times 5 is same as 5 times 2, right? So it would still be. In fact, what we would do is we would try to get them in a way where we could reduce them. In fact, you're probably right. So I know right off the bat this will reduce because I see AB right here, and I see AD right there. And I see not A right there, and I see not A right there. So I know right off the bat this guy's going to reduce. So this is the circuit. This is using all the symbols. So I've got an inverter, not A, not B, and C. Not A, B, and C. Not A, B, and not C, and A, B, and C. And then I started doing math. I started grouping them. And so the circuit I came up with, this is the circuit for that equation, for that truth table. And the circuit I came up with would look like this. So I'd have A and B. Its output would feed an OR. And then I would have A, so I'd bring A down from here. And bring it into one end. I'd bring A down to here. And bring it into the other end. And then I would bring in not C. No, I'm sorry, it's not A. So this would be inverted, not C. So this is the circuit I started off with. This is what I saw in my head when I was designing the scale. And then he took that and reduced it down to something like that. So this is the power, guys. So, and a lot of the rules you learn in algebra will apply to this. So you're saying, why do I have to learn how to do this in algebra? Well, if you're in digital and you're designing circuits, because you'll come up with something in your head. You'll draw all this stuff out. And then if you can develop an equation for it, and then do what? Then reduce it, then you're actually reducing the circuit. Y'all should have seen that. I wish I'd have had it. I don't know if I still got the actual circuit. So that's the actual end circuit right there after it's been reduced. Are we going to reduce equations in this class? No. But what I want to show you is that this would be really important if you were a designer. So you get something in your head, you draw it out, then if you can put it in an equation and it reduces, you're actually going to be reducing hardware, right? So this is a NOT. We've already looked at that. The symbol is called an inverter, but the logic is called a NOT. So if you hear somebody say that, well, that's nothing but an inverter. So how would I get that with a relay contact? So what would be a relay contact that would give me a NOT? So if I was to come up here and I was to put some control device like a push button, and I'm going to come over here and use a relay, and I'm just going to call it R. And then I'm going to come down here and put a light right here. When the button's pressed, when the button is not pressed, I want the light to be on. When I press it, I want it to go off. What type of contact would I put right here? So that's a NOT. A single, normally closed contact. But you got to understand the contact is being closed, being controlled by something, right? Understand? So that would be a NOT. You okay? Yes? Oh, I need to call this R. I'm sorry. If I'm not pressing that button, so this rung is false, this rung is true. Right. So it's inverted, right? That makes sense? Yes or no? Yes. Yeah, so when this rung is false, this rung is what? True. When I press that button, this relay coil comes in, opens that contact. So when this rung is true, when I close this rung down here goes what? Oh. So when you look at the contacts, you got to understand it's not the contacts, it's how we wire what's controlling those contacts. So this is a symbol for a 2-input AND gate. Now normally when we teach gates, these multi-input gates, we do 2 inputs because that means we only have 4 entries in our truth table. But so AND gates is a minimum of 2. Right? You understand? Well, I mean, I could have 8. The only problem if I have 8, then there's going to be 256 entries in my truth table, 2 to the 8. So I'm going to come up here now. Now I'm going to have 2 inputs. And we'll call this relay 1. And then I'm going to call this relay 2. So I'm going to have 1 light, because I got 1 output. What do I need to do to get an AND? So I want, when this one's true, and this one's true, I want my light to come on. So am I going to hook the contacts in parallel, or I'm going to hook them in series? If I hook them in parallel, then I could press either button. So yeah, so I'd come over here, and this one would be controlled by 1, this one would be controlled by 2. And now when this one's true, this contact will close. When this one's true, this contact will close. So 1 and 2, when 1 and 2, or when all the contacts are closed, then the run goes through. This is an AND. So if I came over here and added another contact, I'd have to come up here and add another control device, right? You understand that? And then I'd just put another contact in series. So to get AND logic with contacts, we use normally open contacts and we put them in series. And this would be the logic symbol. So it's a D shape. And it's just like controls. Inputs on the left, outputs on the right. So it's just like our are we okay? Okay, OR. So a 2-input OR gate, gotta have at least 2 inputs. That sounds like a good test question. How many inputs can our OR gate have? At least 1, 2. So like I said, I just added another contact up there, and I could keep adding contacts and hook them in AND. Right? So here I want, if A is true, so I'm gonna call them the same thing now, guys. So I'm gonna come over here and put a switch, and I'm gonna call this relay A. I should have done that before. And then I'm gonna call this relay right here B. So there's my 2 inputs. Oops, I need to put a circle down there. So I want that light to turn on when I push either energize A or B. So how am I going to hook my contact? There's OR. So we use normally contacts in parallel to get OR logic. How many contacts can I have? At least 2. And like I said, normally when we teach this, we only use 2 inputs on these OR gates and AND gates because that only gives me 4 combinations in my truth table. But I go ahead and add, if I have 1 more input, now I jump up to 8. If I have 4 inputs, now I got 16 inputs, right? If I have 5, now I've got 32 entries in my truth table. So truth tables are nice. Truth tables are nice, but if any input If any one of those contacts are closed, then the rung will be true. So that's probably better than for you to know than truth table. Everybody understand that? This is a NAND. This says all highs equal to low. You can see the truth table. All highs equal to low. So what we're going to do with NANDs, NORs, and NOTs is we're going to make the rung go false. So what's required for the rung to go false? ANDs and ORs are what's required for the rung to go true. So, let's see. So these could be controlled by the sensors. Right now we're just using a push button. And we could hook these up. We could program them in no time. So I got this guy right here. I got two inputs. We'll call this input A. And I'm going to call this input D. Or relay D. So I want the rung. This is all. So we're saying all inputs, right? So how would I get a NAND? A NAND, I'm sorry. So that means I have to press both of these buttons before the rung goes false, before the light goes off. So I'm going to use normally closed contacts. Here's my light bulb. Then I'm going to come down here and do this. Here's A and B, and that's a NAND. So my rung starts off what? True. And how do I make it go false? Both of them or all of them. So this gets people messed up because they come up here and they see this, and we call this an OR. And now they got that in their head. And they will come over here and see this, and they want to call that an OR. But it's not. So normally closed in parallel, this is a NAND, right? Everybody understand that? Okay, we'll see. When I put that on test. These are going to be on next test, by the way. So NORs, we want any to cause the rung to go true. So these NANDs and NORs, the rung starts off true. And what's required to make it go false? So here's A, here's B. So this guy's going to start off true, and if I press either one of these buttons, I want it to go false. So I got my light over here. By the way, if you take motor controls, anybody take motor controls right now? You'll wire up these circuits. And you'll do push buttons. You'll do exactly what we're doing up here. And you'll only use two. So you're going to wire this up. We're going to do the logic. So this right here is a NOR. So the rung starts off true. And if I press any button, the rung goes false. So normally closed contacts are a NOR in series. Normally closed contacts in series is a NOR. Normally closed contacts in parallel is a NAND. Normally open contacts in parallel is an OR. Normally open contacts in series is an AND. And a normally closed contact by itself is a NOT. So a NOT is only one contact, right? You understand that? So this is not two NOTs. And then we can combine logic. So, you know, I could come up here and do this. This is just the logic. And then I could come down here, and do this. Of course, this wouldn't be no good. See, so what we have, this would be not A and B, or A and D. Of course, this down here, that one would be true all the time. But what I'm trying to say, we can combine logic in a row. And we'll see that all the time. This is an exclusive OR. Now, what this guy does, it looks for equality. So these are our comparators. In digital, this would be made up of about 4 or 5 gates. You notice it's different. It's got a ghosting input. So an exclusive OR and exclusive NOR will have 2 inputs. No more, no less. This is not an OR, it's an exclusive OR. And what the output is telling me is what I get when the inputs are not equal. So notice when the inputs are not equal, I get a what? I get a 1 or a true or a false. If they are equal, I get a false. So right off the bat, I know when they're equal or when they're not equal, depending on what I get out of the run. So how am I going to do that with contact? I'm not going to draw the relays. I'm going to call this AB. I'm going to call this AB. Oops, sorry. I'm going to do this. So if my 2 controls, so what you got to do now is you got to picture this. You got to picture what's controlling those contacts. Oops. Here's A. Here's B. So when you look at the contacts, you got to understand something's controlling those contacts. So right now, my 2 inputs are equal. So these contacts would be in the state they're showing. So it would get through with A, but it wouldn't get through with B. It wouldn't get through A, it get through B. So I start off with 2 zeros. I start off with a 0. Okay, so let's say I press A. When I press A, I'm going to circle them. This contact right here would open, and this contact right here would close. So now they're not the same. So what I'm doing is I'm pushing down on this button. So now my 2 inputs are not the same. Now, so what's happened is I've got this path right here, and I've got a short circuit. Let me put my light bulb right there. So let's say I let go of A. Okay, and let's say I press B. I'll press B. So A is going to be open, so it's normally close contact with here. This right here would close, right? Understand? And this would open. But now we got a path right here, and the light would be on, and they are not equal. So now B is true and A is false. So let's say I come up here and close both of them. Okay, so that's going to open this contact here and close that one. This one's open, and the output goes off. So an exclusive NOR, an exclusive OR tells us when we're equal, right? But this guy gives us a 1 when they're not equal, and it gives us a true when they're not equal, and gives us a false when they are equal. And so this is our comparator. We do that all the time, comparing when something is equal or not equal. Except this one gives, and this symbol tells you what you get when they're not equal. So this is an exclusive NOR. So notice here, we get a 1 when they're equal, or we get a true when they're equal, and we get a 0 when they're not equal. So how am I going to do that with contacts? Two contacts, exclusive ORs and exclusive NORs, only have two inputs. An OR gate can have at least two, right? You understand that? So I'm going to start off with the same circuit. By the way, when we're taking our classes in Germany, that's one of the things. Can anybody, that's what he said, can anybody draw how you hook contact to get an exclusive OR? And of course you don't. Of course they got what they wouldn't even call me anymore, by the way. That's true. You can ask Nancy that. Okay guys, so this is what we do. I'm not drawing the control, right? I know we got two controls. So A and B, but I don't have the button pressed, so they're both false. So they're both here, and the output would be true. If I press A, then this contact is going to do what? It's going to open. This is going to close. Okay, so if this one opens and this one closes, B is still closed, so we get that one. If I press B, then this contact's going to open, this is going to close, but A is closed here, this is open, so I get this one. If I press A and B, then these two open, but the top two close. So that's the way we would wire contacts to get an exclusive NOR. How many inputs will an exclusive OR and exclusive NOR have? Two. No more, no less. An inverter would only have one. No more, no less. Your ANDs, your ANDs, your NANDs, your NOTs, and your ANDs, your NANDs, your ORs, and your NORs have at least two. And then we can combine logic. And then, so this is on there, by the way. This is the way we would program in function block diagram. So here is the ISO or the IEC, the International Electrotechnical Commission. These are international standards. These are ANSI, which is the American National Standards, right? Huh? Yeah. So this is what we program PLCs in. We don't use these, which is what the book teaches. This is what we use. So notice, and this right here is an OR. Greater than or equal to 1. So if the inputs are greater than or equal to 1. This is a NAND, so the little triangle indicates the output is false when these two inputs are true. This is greater than or equal, if the inputs are greater than or equal to 1, the output will go false. Here's an OR, if the inputs are equal to 1, right? Here's an exclusive NOR. I need to look that up. I don't think it's right. Because this will give us a big problem, right? This is a NOR. No, this is a NOR. So if the inputs are equal, then the output would be low. And if the inputs are equal, so this is an inverter. Where's our choices? Oh, these are equal. So if the inputs are equal, well, the output would be out. What's wrong? I need to look this one up. Because an OR, an exclusive OR, we get a 1 if the inputs, it looks like they've got these two things. or an exclusive we get a 1 when they're not equal. For an exclusive OR, we get a 1 when they're not equal. Right? An exclusive NOR, we get a 1 when they are equal. So it looks like these two symbols right here are reversed. So here he says we get a 1 if they are equal. Here it says we get a 0 if they're equal. So I think these are reversed. For the exclusive OR, we get a 1 if they're not equal. And exclusive here, we get a 1 if they are equal. So yeah, I think these are reversed. I'll go back and make sure I set that.
It's down at the bottom right there. In the bottom of it, you talk about the
Yeah, but they're also reversed. But see, exclusive OR, we get a 1 if they're not equal. This says if they're equal, to me indicates that they are equal. The exclusive OR gives us a 1 if they're not equal. Exclusive OR gives us a 1 when they are equal. So it looks like these two symbols are reversed. And I don't know if I got this table off the internet or if I've cut and pasted them in there, then I got them wrong. But I need to look at that. So guys, we're not going to teach Karnaugh maps. This is what Nancy likes. And Karnaugh maps is another way of reducing. But it's just like a truth table. The more inputs you have, your Karnaugh maps get big. So Karnaugh maps works okay for up to 4 inputs. If you get over 4, so we're not going to teach reduction at all. What you do is look for matching ones. Because Nancy loves this. I like algebra. I like the algebra. So the algebra works. And that's it. So we're not going to do any reduction. We're not going to look at Karnaugh maps, but you are going to be able to identify the inputs, right? And one of the labs that you're going to do is you're going to have to, by the way, did I give y'all the lab procedures in this class? Yeah, I think I did. Yeah. It gives you the labs we're going to do. It gives you some corrections that you need to do in the lab book. So you'll need to make sure you reference that. All right, guys. Any questions? Y'all want to talk about the logic? Got any problems? Yeah, if y'all taking digital, y'all rip that up. And what we teach in digital though is we teach the ANSI, the American National Standard Institute symbols, because that's what you'll run into in digital circuits. But in PLCs, they use the IEC symbol. So, but you can draw the circuit out and you can program. It's really neat. I got some programs, but they're not. This guy right here doesn't support function block diagrams. The only language RSLogic 500 supports is ladder. But the RSLogic 5000 supports all of them, but what they call it, the instruction list. I don't know if anybody programs that. All right, guys. Y'all can take a break if you want to, and then we'll be in lab the rest of the class. So let's see what labs we can do. I know y'all working on some of your homework labs, which you should have turned in, right?